fourth session of the day already. And again, I believe we are going to be addressing something which is really cutting edge today. I'm very, very happy that we managed to schedule this session with Professor Kasper Moth-Poulsen, who is just joining us today. Hello, hi there.
Hello.
Professor Moth-Poulsen has been working on some cutting-edge technology to make long-term solar storage possible. This is a topic that has come several times. Different applications require different kind of storage, length of storage, but the possibility of being able to store energy for a long time has so far been a relatively big challenge. Should I dare to say until now, Professor?
Our ideas are not on the market yet, so there's still some way to go. So, but of course, we are optimistic about what can be developed and how it will look in the future. So, I'm very thankful for your kind invitation to present some of my thoughts and ideas here. I don't know if I can control the presentation or you will do it for me, or how does it work here?
Yes, you can control it. You can simply share your screen and your presentation and then manage your presentation and I will disappear.
Okay, brilliant. So thank you very much, John, and also Leonci for organizing this conference and inviting me. My name is Kasper, and I'm a research professor at the Institute of Material Science in Barcelona, and also Chalmers University of Technology in Sweden. And what I'm going to talk about today is a class of materials that we are developing that may lead to new opportunities for controlling temperature. We call it solar thermal management materials or molecular solar thermal systems. But before I start, I'll just give a brief introduction to how we are thinking about energy and why we are doing this. So this is supposed to be a picture of a polluted city, and we have pollution all over the world, and even in Sweden, which is a very big country with relatively few people, we have 7,600 people dying too early each year due to air pollution. And if we look at European level, we have around 800,000 people dying too early, and on average people lose 2 years of their lives. Now, I don't know the numbers from Africa, but I assume that it's even though it's a very big continent, that with very big variations in pollution levels, that this could also be a challenge there. And I know that the numbers in China is about the average of 8 years of lifespan lost due to air pollution. And India even more. So this is a serious challenge that we have to work on getting around. And this air pollution comes from burning things such as wood, coal, oil, and gas. So luckily we are in a moment of transition, and a lot of solar cells and wind turbines are being made. But we need to be able to store the energy from when the sun doesn't blow, or the sun doesn't shine, or the wind doesn't blow. And these are imminent challenges for material science and also companies and our societies. But what many people are not maybe aware of in this context is that electric power are only a small part of our total energy use. If we look at the end use of energy here in EU, then 48% of the energy is used for heating something. That could be for cooking, heating houses, in the industry, and so on. So we spend half of our total energy mix on controlling temperature and making things warm enough to do the things we need. And majority of this energy is coming from burning fossil fuels or burning other sources of energy like wood or biomass. So the other 52% are going to transportation and electric power. So our work is focusing on creating alternatives for these fossil fuels. We would like to be able to make higher temperatures or control temperature without having to burn anything. So how could we do that? How could we store solar energy without emissions. If we look into so we are chemists. So what can you do with chemistry? One of the things is you can plant a forest. It takes very long time for the trees to grow, and we are many people on this planet. So it's not guaranteed that planting more forest will lead to enough energy to sustain our energy needs, and the efficiency of the photosynthetic system are also not very high. Then there are different artificial variants of this, where you can create hydrogen or methanol or other hydrocarbons from CO2. But altogether, these systems still need exchange of materials when you extract the energy from them. So therefore, we are trying to develop something completely different that we call the molecular solar thermal system, which is a fully emission-free alternative to energy storage. So how could it look such a system? The basic idea is that there should be a starting material, we call it the parent molecule, that absorbs sunlight. And when it absorbs sunlight, it undergoes a photochemical transformation into a new molecule, we call it the photoisomer. This is in a way a transformation similar to what we see in the plants with the photosynthesis, that the light is used to drive a photochemical transformation and something new is formed. The special thing about our molecules are then that instead of burning them to get the energy out, we can trigger a heat release and recover the original molecule in a so-called closed cycle, where the only input is light and the only output is heat on demand. Throughout the cycle, the material is cold, so there's no heating involved except for when we release the heat. So this is it has several possible advantages, such as it's a closed system. It can have high energy densities, long-term storage, and we don't need any insulation material, and we create the heat once it's needed. The only problem is that this material does not really exist today, or it's still under development. So the basic idea dates back more than 110 years, and still today, some of us are working on developing efficient materials that can do this cycle. So let me give you a story about how we have been developing these materials in my research group for the last 10, 12 years, and also how we are thinking about using these materials in future devices or machines for that utilize this energy. So the material we're working on is called norbornadiene. It's a derivative of a natural product that was found on Borneo originally. And when you shine light on this, new chemical bonds are formed, and we form a molecule, the pink one here, it's called quatercyclane. And the quatercyclane is 1 megajoule per kilogram in energy higher than the norbornadiene. So this means that we can store quite a lot of energy in this reaction. And then when we need the energy out, we can transform the molecule back and release heat, for example, during the nighttime, or when we have a certain amount of heat that we need. The challenge here is that this system that are commercially available can only absorb UV photons, and the process is not really that efficient. So I've spent the last 10, 12 years on engineering this system, trying to improve different important factors, such as the so-called photochemistry, the energy storage capability, the heat release reaction, and also how we make these systems so that in the future it will be an affordable technology. So some of our goals here was to make the molecules better in absorbing sunlight, ensuring that the molecules could store energy for long periods of time, and to have an energy density that was at least better than storing heat in water, in hot water. So it's at least 300 kilojoules per kilogram was our goal. And when we started, there were some examples from early discoveries in the 60s and the 80s on different ways to try to achieve this. And one of them, made by Yoshida here, had different components, so-called donors and acceptors, in order to match the solar spectrum. But as you see here, there are 4 components on one storage unit, and this made the energy density go down significantly. So in the next 5 minutes or so, I will I will give you a little bit of introduction to how we work and how it is to develop new materials using organic chemistry. I know that many of you are not maybe not chemists, and but I will try to give you an idea about how we work and what can be done when you spend a lot of time on engineering molecular systems. So how we work can be shown here. We normally start with some idea, either from just something we have been thinking of, and then or something that is helped from computer calculations. Then we go into the lab and make something, and then we evaluate the properties, and then finally, if it works really well, we test the material under different test conditions to see how well it works, and then we learn from that and do a new cycle of new generation of molecules, and hopefully one day it will be good enough for many of us to use it in our daily lives. So one of the first challenges we had was that the norbornadiene, it did not absorb sunlight. It absorbed only light in the UV range. So this is a graph that shows the color of the sun, different wavelengths, and we have a maximum of the radiation between 500 and 600 nanometers. That is in the green light, and that is also where the plants absorb light. Interestingly enough, so the green plants are optimized to work where the sunlight is most intense. But our molecules were only active out here in the left part between 300 or 400 nanometers. So how could we improve that? And we wanted to do that while keeping the other requirements there. So our first design was a simplification, you can say, of what was done in Japan in the 80s, integrating a so-called donor and acceptor unit on one side of the molecule, and in this way trying to improve the optical properties, improve the color, and at the same time keeping the energy density as high as possible. So in the first series of compounds, we put so-called donor and acceptors. These are these rings here, and we're able to significantly improve the solar spectrum match and the photophysical properties. But it came at a price because the donors and acceptors were quite heavy, and this means that the overall functionality of the system, the energy density goes down from about 1,000 to 270 kilojoule per kilogram. So in the next generation system, we changed the acceptor for something very small, only one carbon and one nitrogen atom sitting here. And with this new series, we were able to reach much higher densities, because now the donor acceptor system only weighed something here and a little bit. Let me just see if I can. Made something here. It is benzene ring and a donor unit with a nitrogen here, and a small acceptor unit with a cyanide group. And these new molecules satisfied fully our target on energy density with up to 629 kilojoules per kilogram, which we could measure in some instruments at our university. So this is more than twice our original goal. So after some years of work, we also started to test the stability upon cycling. I mean, we just heard the previous talk that battery technologies, you can charge your batteries and you use them, but after some number of cycles, they will start to deplete and the functionality will go down. And this is the same for our system, that we wanted to test how long can they operate. And here we have each point here, each blue dot is one reaction, and we have here 125 storage and release cycles with almost no degradation. So under optimized conditions, this system can be made to store and release energy in many times. So these are some of the key characteristics of this molecule. It could store a lot of energy, around 400 kilojoules per kilogram, it had acceptable optical properties, and we could cycle it many times without degradation. But then comes the problem that it's difficult to get all you want. And in this case, the storage time was only 5 hours. So this was not much of a storage system. So ideally, it should of course be much more than that. So today I have a little bit limited time, so I cannot tell you the whole story about how we engineered the system further to not only have the optical spectrum and the energy density, but also the storage time. But I will just fast forward to 5 years later and say that today we have made systems that have even higher energy density, up to 0.9 megajoule per kilogram, and can store the energy for up to 18 years by doing small detailed variations to the molecular structure and learning about how they work and how to improve them further. So with these molecules in hand and these new materials available, we have started to study how we can make them work, how we can capture sunlight in an efficient way and release it later as heat on demand, and what it can be used for. So how can this be introduced into devices? So one of our first problems, I know I told you that we were improving the solar spectrum match, but our molecules back then, they could still only absorb a small part of the solar spectrum, up to the orange part here. So we needed to do something about the rest of the sunlight. And this is a general problem, not only for our system, but also for solar cells, that photovoltaics, that you cannot use the full spectrum. There are some fundamental physical limits to what you can do. And the solar spectrum spans not only the visible, but also the infrared part. So how can we use that? And in this experiment, we decided to combine our molecules that are semi-transparent or transparent to all wavelengths above 400, to combine that with a water heating system that we could put underneath. In this way, we could utilize the high energy photons for the energy storage, and the rest of the photons, the low energy photons, go into water heating. And by doing this, we could actually utilize 80% of the incoming energy. In this case, most of it goes into water heating, but with future development, the amount that is stored in the chemical system are to be improved. We could also build somewhat larger scale devices. This is a test setup from the roof of our university that we made some years later. Another part we wanted to study was how to get the energy out of these systems. And here we had some design challenges again, because the molecules themselves are like a white or yellow powder, and they need to be liquid to be pumped through these devices. So we needed to find a carrier fluid and also have a big amount of molecules in the fluid. So we again, with some engineering and a lot of hard work, we came to what the students called the super molecules that could be dissolved to a great extent, and also should be able to heat something by a temperature gradient of 65 degrees with these parameters that we measured. So this is the first device that we built. It has a small tubing where the molecules come in, and a catalyst center in the middle, and then a tubing where the molecules come out, and then we are measuring what is going on in here. And much to our delight, the molecules actually released the heat, and we could see a temperature increase of 50 degrees in one of our first experiments. So this is from room temperature up to around 75 centigrades. And with more engineering, we could go up to 85 degrees, which is the current world record in such systems, and shows that we're not so far from being able to boil water or even higher temperature things. And this is something that we are currently working on. We can also try to operate the systems again for a longer time. Here we did 50 cycles where we used the catalyst and some light source to drive the reaction and release the energy, and show it can be running for extended periods of time. One of our recent developments is to combine this local heat production with a so-called thermoelectric generator. And the thermoelectric generator transform a thermal gradient into electric power. So if you have a hot site, heated by our molecules, and a cold side that is these aluminium brick that is radiating energy out to the surroundings. Then you can create electric power locally on demand without the need for electric batteries or photovoltaic cells, using our very simple material instead. So in summary, we have developed these materials. We can make solar capture devices, heat release devices, and even devices that can convert heat into electric power. One little last thing in the last 1 minute or so, I would just share with you another idea that we have and we are currently exploring is if we look at windows, we often have the problem that the sun is a very powerful source of energy, and we want to sit indoor and have a comfortable climate, but we also would like to look outside and make it feel like we are outside. So that's why we have windows. But during the day, the sun is so powerful that our rooms now often get a lot of heat, and it gets too hot inside, and therefore we need to roll down blinds to block out the sun. But then the window is not a window anymore. The blinds are not transparent. So could we maybe use our material to create a more transparent situation and mitigate these daily changes in temperature? So this is a graph that illustrates the problem that the black curve is what we have. We have a lot of heating during the day and then cooling during the night. And we would like to have a stable, comfortable indoor temperature of maybe 20 some degrees. So what we are trying to do with our material is to use it to store some of the energy during the day and then release it during the night. And here is a picture of a first miniature window panel that is containing this yellow compound. And when we shine light on it, it is converted and becoming fully transparent. And then during the nighttime, it's releasing this energy and recovering into the yellow color again. So here's a little picture of a first prototype where you see how it's yellow first, and then out in the sun, it's capturing energy, it's changing color, and then during the next 4 hours or so, it will 4 to 8 hours, it will release heat, and this is then contributing to lowering temperature during the day and increasing the temperature during the nighttime. Still, with the molecules at hand, these are quite small amounts of energy, so we store around up to, with our current system, between 10 and 30 megajoule, 10 and 30 watts per square meter, and release a fraction of that over the course of the nighttime. So we still need to improve the materials to reach commercially meaningful energies, but we're working on it, and hopefully one day we will be able to provide materials that can mitigate the daily changes in solar influx and temperature variation. So this is also now a part of a startup company that we are working on to develop these materials. We are also working on scaling the technology and accelerating it towards real applications together with different companies and research institutes here in Europe. With that, I hope I have taught you something, or maybe inspired you about how we are thinking about energy, how we're working with capturing solar energy, trying to control the temperature and produce upgraded heat or electric power in new ways that were not possible before. So thank you very much for your attention. These are some of the collaborators and sponsors of different materials and technology. And thank you for your kind invitation. These are the people who have done the work, the current and past group members. Thank you very much.
Thank you so much, Professor, not only for the work done, but also for managing to summarize 10, 12 years of dedicated work into a very, very short 30 minutes presentation. That's also a great achievement. there were a lot of comments there. You know, you said, "Oh, maybe this is a bit too complicated," but we have a great audience today, and we had some great interest. On my side, I'm totally not a chemist. I totally believe you on everything that you've presented. And I'm a bit more down to earth, and I wanted to ask you a question about, okay, so you're working on this technology. Yes, it's still work in progress. You're still optimizing things, even though you've optimized it a lot. But what do you expect could be applications for us in our day-to-day life? You've presented the windows. Okay, I can picture my window. I can imagine this. Are there any other applications that you are currently dreaming about or anticipating?
Yes. So one of the things I'm dreaming of is local power production. I think that is like we have a lot of devices that requires charging, like these headphones here. What if I could get rid of the cable and have a automatic charging system where it's automatically charged either by the heat from my head or by going into the device and using thermoelectric generation, or through sunlight hitting maybe a material like we are building now, and then ensuring that it's recharged automatically without us having to use external power. I also hope that we can scale this a little bit more so that the energies become meaningful for maybe charging smaller devices or off-grid applications where it is too complicated to roll out a centralized power supply from. So I think we see a lot of development like that today with batteries and photovoltaics, and it's really exciting. But it could be that there are challenges when we start to scale these technologies in terms of what materials are being used. Are there enough cobalt for the batteries? Are there enough lithium? And therefore, I think it's stimulating to try to explore something completely different. And that's what we're doing. And by the way, thank you for the comments. There's one person who says that this type of windows have already been invented. Please send me a link to that or an information about that, because I'm not aware of that. And the term molecular solar thermal is something that we initiated in our research. So we made up the term. So I would love to see examples of these windows if they already exist. Or maybe there exist alternative ways of doing similar things, and that I would love to learn about. So please send me a link or drop me a line about what you're thinking of. That would be very useful. Yeah?
Thank you, and thank you for the comments of the listener. Maybe one last question, if you allow me. So you're still working, you're still optimizing this technology. You're dedicating, you and your team, all your time to this. What is necessary to achieve your goal? Is it a question of time? Is it a question of funding? Is it what is the challenge now?
Yeah. So it's difficult to know exactly what is needed. So because it's very difficult to predict how to make the big leaps forward in innovation. So we are of course trying our best, and we have really improved the system a lot. But I cannot guarantee that if you give me €1 million of research funding, that I can guarantee that I will achieve this much improvement. So what it needs, I think, is some more breakthroughs, some more good ideas, and more people working on it. And then little by little, performance are coming up. And when we started, I think we could capture in the first devices 0.05% of the solar energy, and now we are at 3.8. So we have improved 80 times in these 10 years. And of course, we cannot continue improving that much, but maybe with a little bit of engineering here and there, suddenly we are at meaningful performances. And then we are, of course, thinking about how to scale this and how to produce this in a cheap way. So it's difficult to say exactly. We're doing our best and trying to attract funding from different sources, trying to inspire others to work in similar directions as us. because we cannot do everything ourselves. So today there are several groups in the world working with this, and this is great to see. And I hope together that all the many researchers working on this type of things, some of the ideas will work well enough to meet the market demands. If you look at other technologies like batteries or solar cells, for many years, a solar cell was something on a pocket calculator that could recharge the little pocket calculator, and that was because the price was too high and the performance too low. And suddenly, it became there was some breakthroughs. And suddenly, it became cheap enough. So now we can put solar cells all over the place, and they're likely the cheapest way of producing electric power today. I mean, it's a fantastic revolution, but it took 50, 80 years maybe. And that's because they had to compete with existing technologies, and they had to be better, and they had to be cheap enough. This will be the same here. It will take some time, but hopefully not 50 years, hopefully less than that.
Well, that is what we are wishing you and your team to make happen. I would like to thank you once again for making the time today.